So I felt that these last few slides were a bit rushed during lecture. If you understood them, you don't need to watch this video, but if you felt like you didn't quite understand what we talked about during the last 15 minutes, I will try to reiterate it here a little bit more slowly and more clearly. Okay, so any force for which there is a corresponding potential energy function is called a conservative force. And as mentioned in class, both gravity and spring force are conservative forces. So for gravity, our force of gravity is equal to mass times the acceleration due to gravity in the downward direction. And the potential energy function for corresponding to this force is mgy. Similarly, the spring force is minus kx, where x points in the direction of either which way the spring is being stretched or which way the spring is being compressed, and this minus sign just tells us that the force due to that spring is in the opposite direction. And the corresponding potential energy function for a spring is 1/2 kx squared, where k is our spring constant, and x is how much compression or stretch we have, how much stretch / compression, of the spring we have. And there are also non-conservative forces. These are forces that dissipate energy. Examples of these are friction, air resistance, also known as drag. And it's hard to, so basically when you get, when dissipative forces are involved, it is hard to get the energy back, so to speak, because it's being dissipated into a form that it is very hard to harness the energy from. It's, in some cases, it's possible, but oftentimes very inefficient to try to reharness that energy back. For example, let's say I have a block that is being dragged along the floor with some friction between the block and the floor. As this is happening, there might be some thermal energy that is heating up, so thermal energy that is heating up the surface of the floor and the box, and that energy is, so to speak, dissipated because it's going to be very hard to then reharness the heat between that's being generated in the floor surface and the box surface and put it into a form of energy that is then usable. All right. Then the next distinction I wanted to make clear is the fact that the work done by conservative forces, so the work done by gravity, the work done by a spring force, is independent of path. So for gravity, let's say you're putting your book, let's say you have a book on a table. So here's our table, and let's say you have some books sitting on here, and then you have your bookshelf in your room somewhere over here. Okay, there's your bookshelf. All right, anyway. And let's say you want to move this book from the table to this part of your bookshelf. Now, if you take that book and first put it on the floor and then put it up here, the net work done by gravity is the same if you just take the book and directly move it here. Or if you take the book, put it on top of the bookshelf and move it to this level. Or you take the book, you go for a walk, you throw the book up and down, and then you come back and then you put the book here. The path you take to move the book from here to here doesn't change the work done by gravity on the book. On the other hand, non-conservative forces are dependent on path. So the work done is going to depend on the path you take. And as mentioned in class, let's say you are analyzing how much work is done by friction as you move around a box, let's say from point A to some point B. Well, one path you can take is just go straight from A to B. Another path you can take is you can go to somewhere in the between, come back, and then go to B. Each of these paths has a different amount of work done because dissipative forces or non-conservative forces, it depends on the path how much work you end up doing. All right.